Welcome to Lee's Science Academy, a study room where you don't just memorize but understand systematically and logically through the whole picture. We will try to organize the content well so that your precious time is not wasted. This channel delivers basic knowledge of natural sciences logically and systematically, which is good to have before starting your major studies in college. It is not a lecture focused on simple memorization. In short, it is a channel for studying. Of course, it will also satisfy the intellectual curiosity of the general public who want to systematically understand natural and biological phenomena. In the last lecture, we created natural numbers through abstraction. We also learned about the operations on natural numbers, which create new natural numbers from them. In addition, we studied the closure and openness of operations depending on what kind of number the operation result is. An operation is a calculation process that uses numbers to create new numbers according to operation rules. If you follow the operation rules faithfully, you can eventually find the answer, even if it takes some time. However, since doing calculations quickly is very important in actual calculations, let's look at the operation rules that can be applied to the calculation process of natural number operations. Here is the overall lecture content regarding the operation rules. There are various operation rules applied to make calculations fast and easy, but as representative operation rules applied to the four basic operations on natural numbers, we will study the commutative law, associative law, and distributive law, and look at the order of operations, which is the order in which operations should be performed when various operations are mixed in actual calculations. Operation rules are almost intuitively understood and accepted as they are, but in the process of studying, it is necessary to analyze their contents and prove them directly at least once. I hope you take that opportunity here. Today, in the first video, we will only cover the commutative law. The general definition of the commutative law is that when a binary operation is given in a given set of numbers, it holds true if changing the order of the two elements being operated on does not change the operation result. In the case of performing the four basic operations on natural numbers within the set of natural numbers, the commutative law holds for addition and multiplication, but not for subtraction and division. How can we prove this proposition? Since cases that do not hold are negative cases, showing a counterexample is sufficient. I will prove the non-establishment first. In subtraction, subtracting 3 from 5 yields a different result than subtracting 5 from 3, so the commutative law does not hold. In the case of division, changing the dividend and the divisor also changes the result, so the commutative law does not hold. Since the commutative law does not hold in subtraction and division, in actual calculations, the order of the two numbers must be strictly kept according to the calculation purpose. You also understand that subtraction and division are not closed, so you have to check the calculation result every time, right? How can we prove that the commutative law holds for addition and multiplication? The proof of the commutative law can be judged as true or false by actually calculating it directly according to the definition of the commutative law. Adding 5 to 3 and adding 3 to 5 yield the same result according to the definition of addition, so by the law of identity, which states that identical things are identical, we can see that the commutative law holds. In the case of multiplication as well, multiplying 3 by 5 and multiplying 5 by 3 both result in 15, so we can see that the commutative law holds. If there are no false cases even after multiple calculations, if there are no counterexamples, it can be said to be proven true by induction, as we said. Even if proven by induction, Induction has limitations regarding the uncertainty of the future, so there is something lacking in mathematics, which requires strict proof. Therefore, we understood in the previous time that the principle is to overcome the limitations of induction and prove all mathematical propositions by deduction. As mathematics, which is a 100% abstract discipline, becomes true only when it is within a deductive structure, it is proven by deduction. As I said in the last video, all mathematical propositions learned in this channel from now on will be proven, even if it is tedious and time-consuming. So I hope you do not spare your time, do not find it tedious, do not skip the proof process in the video, but follow it to the end and have an experience of proving it directly yourself. You can grasp the logic of numbers and mathematics in the process of proving obvious things. Here, I will directly prove the commutative law of addition of natural numbers deductively. Let's set the universal set U, where the calculation takes place, as the set of natural numbers. Let's choose arbitrary natural numbers a and b. Then, a can be rewritten as adding 1, a times, according to the definition of natural numbers. B can also be rewritten as adding 1 b times in the same way. What we need to prove is the commutative law, so we just need to show that the calculated value of a plus b is equal to the result of b plus a, where the order of operations is changed. I will do the proof directly. I will prove it by showing that the value of the left side and the value of the right side are equal. For the left side, a plus b, since identical things are identical, we change the expression to the sum of ones. The meaning of the right side is that we added b more ones to the a ones we already had. So we count the added numbers according to the definition of natural numbers. We count by adding 1 plus 1 plus 1 up to a, and continue counting as a plus 1, a plus 2, and finally up to a plus b. Then, according to the definition of natural numbers, the operation value becomes c, if we set a plus b as the literal number c. Of course, c becomes an element of the set of natural numbers. This time, let's look at the right side. We will also express the right side, b plus a, as the sum of ones. First, we add 1 plus 1 plus 1 to get b1s. Then, we additionally add 1 plus 1 plus 1 to get a1s. Then, if we count the total number, we can finally count up to c. Then, the calculated value will naturally be a natural number c, according to the definition of natural numbers. Here, we proved that the left side and the right side are equal to c. Therefore, a plus b and b plus a are equal to c. The meaning of this expression shows that the commutative law holds. So the proof is concluded. This time we will prove the commutative law of multiplication of natural numbers. Let's set the universal set U, where the operation takes place, as the set of natural numbers. Let's choose arbitrary natural numbers a and b. Then a can be rewritten as adding 1, a times, as we have done so far. B also becomes B1s being added in the same way. What we need to prove is the commutative law of multiplication, so we just need to show that the operation value of the two terms being operated on, A times B, is equal to B times A, where the order of operations is changed. I will do the proof directly. In the left side, A times B, we rewrite A as the sum of ones. And since multiplying by B means repeatedly adding A, B times, according to the definition of multiplication, we write it out in the form of repeatedly adding A. You understand this expression, right? Here, we will slightly change the expression format for the proof. We will change the horizontal addition to a vertical addition format. Then it becomes a shape like this. You understood that the horizontally written expression and the vertically written expression are the same, right? The sum of all the ones written here will be the operation value. Here, we change the order of adding slightly. First, we gather all the ones at the very front. Then the number of them will be B. In the same way, we gather the next ones. The number in this group is also B. We gather the ones vertically until the end. Then the number of vertically gathered groups becomes A, you understand, right? Then the total number becomes repeatedly adding the group of B1s, A times. This repeated addition becomes B times A by the definition of multiplication, which becomes the right side. Therefore, the left side A times B and the right side B times A become equal, concluding the proof. Did you understand well? Did you understand well? What are the advantages of using the commutative law of operations in actual calculations? Since the result of an operation for which the commutative law holds does not change, even if the order of the terms being operated on is changed, you do not need to be bound by the order of writing the terms of the operation. In the actual calculation of natural number addition, you can write the oggend and the addend in any order without distinguishing them, and in the actual calculation of multiplication as well, you can write the multiplicand and the multiplier in any order without distinguishing them. You just need to write the numbers included in the addition or multiplication anywhere. Because the commutative law holds for the addition and multiplication of natural numbers, we can calculate addition and multiplication easily and comfortably without worrying about the order in which we write the numbers. You understand that we are calculating very comfortably, right? This is the main content of today's lecture. So far, we have examined the property that the result of addition and multiplication of natural numbers does not change even if the order of the terms being operated on is changed, and directly proved it. We also understood that because the commutative law holds, we can calculate addition and multiplication easily and comfortably without worrying about the order. This concludes this video, and the associative law will be explained in the next video. This concludes today's lecture. Thank you.